Okay, then let's assume we'll start a second.
Okay, thanks very much. So I just want to begin, I was thinking about this, and there's a lot of surgery and a lot of titles, and I thought about my lectures, and I haven't done any surgery on anything yet. And then I realized, well, where was the surgery in my lecture series? It's all in lecture 2. Yeah, so, okay, that's the way it is, but let me just say a little bit about the background to the classification theorem I presented last time. So Frank's been emphasizing that surgery, it's not something you take off the box very rarely and use it to solve your problems. It's an incredibly sophisticated series of ideas, and I just want to talk about one area of that, which is manifold classification. So these M7s, 2-connected, that I've been talking about, they're always the boundary of a 3-connected 8-manifold, and another word for that is a handle body. So when Wall was doing this, it's sort of like the background of pre-surgery theory. So what do we mean by that? It means you just take an 8 disc and you attach 4 handles to your heart's content. Okay? Okay, and that, another way to say that is that's surgery on the 7 sphere, on a disjoint union of 3 spheres plus the 4 inside of the 7 sphere. And there's a great paper that still gets used for highly connected 7 manifolds. What we'll prove, or in fact for highly connected manifolds a lot, what invariance should we have here? Well, there's this intersection form I'll write cohomologically, since I've been working cohomologically, and there's this characteristic class. And that's it. So this is a theorem here. Well, I'll just say it in slogans. Wall did it, but it's really Smale. This is sort of like a playground. Just after Smale had proved the H-cobordism theorem, what can we do? And the answer is, well, if I have one, for example, here, if I have one of these connected 8 manifolds, I just have this algebraic data for it. Well, I can build a handle body like that, and then I can embed that handle body in it, and whatever's left over is an H-cobordism, and they're all trivial, so I'm done. So Wall proved that this was really a complete invariant of these manifolds. So in this sense, that's why when you're trying to study their boundaries, you don't want to necessarily go through the surgery exact sequence. You just want to understand these things. So if I've got one M0 here, I know I can sort of go back down to the 7th sphere, and then I can come back out to the 7th sphere. Maybe there's a lot of handles here. They're all 4 handles. W0 and W1. Okay, great. And my goal now here, so this whole thing, all of these are spin manifolds. So this whole diagram comes equipped, including normal data, with maps to B spin, classifying the tangent models. So, and now I know my goal is, so this W here, 1, this is the thing I would like to convert into an H-cobordism. Okay. And the invariants I gave to you last time, these are, so they're also, it could also be that I've got a bit of choice, right? Because if I didn't like the W I started with, I could always add a closed 8 manifold here and go again. So that's, from the point of view of classification, that's a basic sort of slogan. How does it work? And the invariants I presented in the last lecture, it turns out they're exactly the invariants you need. But to discover that, you just find them from the algebra here. It's a more effective way to look at it. But the slogan, so manifold classification, we sort of go in 3 steps. So given M0 and M1, so question 1, let's do it like this. 1, so question 1 is, are they boarded? And if so, over what? Okay. So classical surgery theory says, let's make them bound over a Poincare complex. Let's make them bound over the homotopy type. That's a good thing to do, especially conceptually, but in practice, maybe you just like to make them bound over B spin. So the assumption that these things are 2 connected actually makes all of these maps 3 equivalences. And yes, they're an isomorphism. B spin itself, remember that B spin itself is 3 connected. So this is already relatively good, because once, by surgery theory, I can make this boardism look like the target up to the middle dimension, and everything's beginning to look, well, up to the middle dimension, all the manifolds and the boardism are beginning to have the same homotopy. So, over what? Maybe not, if you want to classify things, maybe not a Poincare complex. And then the next thing you should ask is, what are the invariants of boardisms compared to the invariants of closed manifolds? So what are the invariants of boardisms compared to the extent that you can invariants of so if these are n manifolds, this will be closed on n plus 1 manifolds. Also with the map, reference map to your target space and the bundles up. Okay. But that's just a general philosophy for how you would use surgery theory and the H cobordism or the S cobordism theory to classify manifolds, and that's what went into the classification theory. Okay. Good, I feel better. I feel like I need some surgery now.
So it's now, the result is now that if the signatures of W1 and W0 are the same.
What do we need to do? So here's a nice feature. So certainly we would need, if these were homotopy spheres, for example, we see two invariants we need to control. We need to understand the signature of W, but because, and that would be enough in this classical surgery setting, this target would be V string or something, would be highly parallelizable, but because we've got V spin, we've still got this other characteristic number. So these are the two invariants we would have to control if these were just homotopy spheres. And we bundle that all up into the A-root genus. So that's where this key invariant, key squared minus signature of W divided by 8 came from, or maybe 8 times 28. That's the thing, the A-root genus of a closed spin 8 manifold has to be divisible by 8 times 28. Yeah, nice. If there's more elaborate data, all this other stuff, the linking form, the homology is sort of in there to get a similar picture when, yeah, it's not a homotopy sphere. Okay, so now we're going to start G2 topology. And I want to start by telling you about G2 structures. And it's great because Oscar gave some very nice talks about structures and so forth. And one of the key things about structures is you want to have a number of different points of view on them. But all right, first of all, you probably want to know the group where your structure lives. So G2, this is by definition the automorphisms of the Octonians. So the Octonians, that's a non-associated division algebra, isomorphic to R8. You can now actually identify this also with the spinor representation of S of spin 7. That's also 8-dimensional, so spin 7 has an irreducible representation. And now the Octonians have a canonical element in them, they have a unit, and G2 fixes that. And that unit might as well be a standard unit spinor in spin 7. So this is also another key for G2 topology. This is a key definition of G2. So this is a fibration. This is nicely proven. It's not obvious to begin with that spin 7 acts transitively on the unit vectors in the spin representation, but in fact it does. It's proven in Jefferson-Lawson. So this is a fibration, and therefore we can think of G2 as the stabilizer of a spinor. We want to now take this. This was all completely local. We were thinking of this as being the tangent bundle, tangent plane, sorry, of a particular point in a 7 manifold. So let's take this global. So on the spinner bundle. So that's a bundle that by definition has this spin representation in the fibre and it goes over here. Okay, and remember that this is isomorphic to R8. So if I would now take a nowhere vanishing section, so S is a nowhere vanishing section. Maybe I've done a little quick. What I should say is if M has got a sort of P to M, it's got this is our spin bundle, right? So we fixed the metric, so we had some orthogonal frames. The spin structure is equivalent to a choice of spin bundle. So this is spin bundle, principal spin bundle of M. Okay, and another definition of our spinner bundle is that it's P cross over spin 7 for our construction.
SM is, was it SM?
Maybe this is, I don't know, this is the notation of the spinner bundle. I just
It's a
defined it.
spinner bundle,
Spinner bundle, yeah.
not the sphere bundle.
Not the sphere bundle. Yeah, I don't know if it's yeah. Yeah, all of what I'm going to talk about today, there's a paper with Nordstrom on the archive called New Invariants of G2 Manifolds, and I'm using the notation from that. I don't know if it's great notation, but there you go. Here's the definition of it. It's a very nice, you've got a spin manifold, it's a real 8-dimensional vector bundle of your spin manifold. Now, I can choose a nowhere vanishing section. I'll review this in a second, but there's enough room. Okay, there's no obstruction finding a nowhere vanishing section here. And now, spin 7 is acting here, and I can look at what stabilizes it. So I can just stabilize that. Such a section. Defines. I want to say this is G2 structure. And so what's that? This is a principal, this is Q inside of P. P. So this is a principal G2 subbundle. Yeah, so I should have said, right up here, because G2 fixes the unit vector, it will fix the imaginary Hamiltonian. So they're going to play an important role. We'll have imaginary Hamiltonians. This is isomorphic to R7. So this is a division algebra. G2 acts orthogonally, so G2, in the first case, is acting orthogonally on the imaginary quaternions, and in fact it's interconnected with the way I define it. So at this level, I can define the topological moduli space of G2 structures so in this interpretation, I'll just establish notation, G2M.
Did you just say that any 7-dimensional spin manifold has a G2 structure?
Yeah, I'm about to prove that now, but yeah, but just for obstruction theoretic reasons, there's no obstruction to finding such a section.
And also because S7 is
Yeah.
connected in.
Yeah. So this is the set of sections without the zero section. Yeah. Smooth. And we are interested in G2 structures up to homotopy, so pi naught, so here's a little lemma.
You want to take one to the unit plane?
Sorry?
You want to normalize the length of it, that would give you a compact.
Oh yeah, that's probably good, thank you. Oh yeah, now we can have really bad notation, thank you. Great.
Maybe
Make it blackboard.
maybe you denote spinners by this dollar symbol.
Yeah, okay.
Yeah,
Good.
Yeah.
So the lemma says that this group here, this is my favorite definition of Z, this is canonically isomorphic to the seventh cohomology of M7 with coefficients in pi 7 of S7. So yeah, so you can see 7 is my favorite number in G2 topology.
Canonically?
Sorry?
Canonically isomorphic?
No, non-canonical.
Non-canonical.
Yeah, absolutely. There's no canonical G2 structure that I know of. So I'll just give you the obstruction theory proof of that. And it's also going to be important, I'll give you the sort of relative Euler class spinor interpretation of that, because that's what we'll be using later on. So once we pick representatives, this would be our spin structure. The G2 structure would be such a lift. I'll call that phi. In fact, there'll be a second definition of G2 structure in the final talk. But a phi now is just a lift. There's no obstruction. Finding such a lift, the first obstruction lives in the cohomology of M, with coefficients in pi star, and there's a shift down. But the obstruction, if I now have two of them, the relative obstruction lives in this group here. And moreover, so this is now what I want to talk about. Here's a nice interpretation. How would I realize this definition of the difference element if I have two of these guys? Okay. What should I do? Well, I should take M cross. I'm going to go to the side. So here's a picture of M cross I. Now I'm thinking of this in terms of spinor fields, okay? So S is going to be a spinor field that is equivalent to a G2 structure. So here I'm just going to draw my spinor field S as a nice sort of nowhere vanishing section. And I imagine, so this is S, I imagine that it's here. And in the middle I have this spinor bundle of M cross I. Okay? And as a section, I can just interpolate between them. I might hit the zero section. So let's just interpolate, and as I do that, I'll get a bunch of zeros. And they'll be signs. Everything's oriented. Maybe some will go that way. And so we can define this just to be the number of zeros with sign. So the number of sign zeros in a generic. So in this sense, this is why there's no canonical choice. This is something like, so this Z is a relative Euler class.
Is that the same as intersecting the two sections in the sphere bundle?
Intersecting the two sections.
The sphere bundle is a 14 manifold.
Sounds like a good idea, absolutely, I believe so. Yeah. And of course, this example one, there won't be any G2 holonomy there except for now. So how, if I had G2 holonomy, how would I get a G2 structure? Well, I'd somehow do the obvious thing. I'd have a 7 manifold, maybe with some topology. I'd pick a base point and I'd pick a frame here. So choose a base point and a frame. And then just, have fun parallel transporting my frame over the manifold, okay? And I might end up with different frames by different paths, But because it's G2 holonomy, these two frames that I would get will differ solved by an element of G2. Okay, that's what it means to have G2 holonomy. So that means I can sweep out to the maximal, this unique maximal G2 structure compatible with the original frame that I picked. Okay, so this gives unique compatible. So this would be now thought of as a subbundle of the frame bundle.
If you have such a G2 holonomy.
Yeah, if I have the G2 holonomy. And that happens, but yeah, that's so I like to think of, I like to help geometers out that I'm a topologist and I can handle structures. So I like to think of the G2 structure as a topological trace of the G2 metric. And okay, there's a G, that's the reason why I called this guy here the topological moduli space. Okay? I mean, there's a map from the honest moduli space to the topological moduli space. And at the early stage of development, when you know basically nothing about the geometric moduli space, maybe it's a good idea to look at the topological moduli space.
Following intention of one mod out the pulling back by the pre-morphism or something?
Oh yeah, sorry, this is the pre-moduli space. Yeah, thank you. There's an obvious action. Yeah, thank you. All right, so now we've got G2 structures. So let's build an invariant for them. New, yeah. So this is a very bad pun. As we were happy to find this invariant, Milner had a lambda invariant, Ills and Kuiper had a mu invariant. It was natural to call this invariant the mu invariant, so it fits. It's also a mu invariant. Later on today, I'll tell you that there's a psi invariant, so that somehow didn't fit into the picture, but okay, there's a little bit later on. There's a push out of the mu invariant and the generalized Ills-Kuiper invariant. That's the psi invariant. But to get this, so to emphasize this point about if you want to know anything about spins G27 manifolds, you need to know something about what happens for closed A manifolds. So there's another vibration. And so spin 8, yeah, because it's E8 is even, its spinor representation splits up into 3 bits. It has a positive spinor representation, it has a negative spinor representation, and it has a vector representation. And I want to think of spin 7 as the stabilizer of a spinor in the positive spinor representation. There's a number of ways to embed spin 7 into spin 8. The miracle here is that all of these guys are 8-dimensional. And this only happens, so the vector representation only agrees with these, this only happens in dimension 4 and 8. And that's one of the reasons why, also the presence of the exceptional Lie group is a reason why 7-8 topology is very rich. Okay?
Spin 7 is the isotopic subgroup of...
For my definition, you can define this, for the purposes of this talk, spin 7 is the stabilizer of a positive spinor. These three, there's an outer automorphism, there are outer automorphisms of spin 8 and all these representations get commuted. It's called triality, it's extremely beautiful. I might mention a conjectural consequence of triality for the new invariant later on, or I will. But for now, we just have to deal with this fact. And this is a little bit confusing for me as a topologist. I'm used to manifolds having one Euler number, but an 8-dimensional spin manifold has 3 Euler numbers. Right? So we can, all of these bundles are the same. So there is, there's a positive spinor bundle on an 8 manifold X. There's a negative spinor manifold bundle, and there's just a tangent bundle, and they each have Euler classes. Plus, minus, and the regular. Euler class. And how these things get normalized depends, but we choose normalization so that E plus is equal to, let me get this right, E plus E minus. So this should check out. What's going on here in the background, all of this is happening in the 8th cohomology of D spin A. So I'm now about to tell you a bunch of stuff about characteristic numbers, and at least rationally, this is isomorphic to Q3, where the generators are E1 squared, E2, and this Euler class. Okay? So it's possible to express E plus and E minus in terms of these generators here. Has to be, just as a matter of logic. And this was actually a key input to the project Nordstrom. This was great. We wanted to know if this was a relationship, so some maths physicists had already figured this out. Two maths physicists, Gray and Green. There's a key characteristic class formula here that tells us that E plus minus is 1/16 of P1 squared minus 4P2 plus or minus 8E. Okay? And I don't have a deep insight for why that's true. You just go away and compute it, and that's what it is.
So if you compute it using Crowley theory, it would be the easiest way.
Okay. Let's just do some examples. All right, now I should apply Thomas's game. What's the Euler number of the H sphere? The regular Euler number of the H sphere? Yeah, 2. Very good. Okay, and here's a hint. The H sphere is stably parallelizable, so P1 and P2 vanish. So does anyone want to be brave enough to have an E plus? 1, yeah, great. So this seems like a good definition, right? And then this is cool. So spin 8 manifold has 3 Euler numbers, and I don't know if I was going to set it up, that's how I set it up. A little bit more interestingly would be to do HP2. Okay. So anyone want to tell me the Euler number of HP2?
3.
Sorry?
3.
Great, yeah, it's got a 0 cell, a 4 cell, and an 8 cell, so this is 3. Now it gets a little bit more hairy because, yeah, all right, you can compute it. Actually, P1 is 4 and P2 is 7, and you get the very interesting fact that this is 0. So HP2 has a spin 7 structure, whereas its negative Euler characteristic, I think, is -3. Yeah, it must be -3 now. Okay. So this implies the interesting fact that HP2 emits a spin 7 structure. Because exactly of this definition, having a spin 7 structure is equivalent to your positive Euler number vanishing.
I mean, probably also we can see that these E plus minus of S8s are so because they have the bot element. And that the Atia bot Shapiro isomorph, you get the bot element which has Euler number 1.
Right. Yeah.
You conclude that there's a formula like E plus equals E plus E minus from the lemma, or is that independent reason?
No, sorry, that's independent. It's more or less by definition, you sort out, there's Clifford multiplication relates to 3 spinor representation, and you sort of, you hope you don't get confused about signs when you set up your conventions, and that's how it comes out. That's in some sense slightly conventional, but it's got to do with the way that triality permutes these 3 representations. Yeah, thanks for pointing that out. That's got to do with triality, the relationship between these 3 Euler numbers. It's not the lemma. So a next key step with Nordstrom was that we had to take this. We realized that if you take this identity of Gray and Green and massage it a little bit, so remember that the A-hat genus can be expressed as a polynomial in P1 squared and P2, and the same thing can be done for the, so maybe I should call this the L polynomial, A polynomial. So again, I've got a general policy of not doing linear algebra on the board, so let me tell you what the outcome of that linear algebra is. So here's a corollary, and this is the key driver for us. For closed X. You have the following very beautiful relation. This positive Euler number is given by taking 24 times its A-root genus and adding 3 times its Euler characteristic, subtracting, just the Euler characteristic on its own, subtract 3 times the signature and divide by 2. So that is the consequence that follows from the E plus equals E plus E minus, this lemma of grey and green, and you just compute it on examples, and that's what you see. You eliminate things using these two polynomials, and you get this key equation. Okay, and yeah, this leads us. The new invariant is now going to be a defect invariant for that particular expression of the A-root genus. And what you need to remember here, right, what do we do here? We took a positive spinor field. Let's think of this now as an A-manifold. We use the spinor representation, but we can identify it with a positive spinor representation. We took a field and we saw a whole bunch of zeros. Okay? So this difference element, that would be E plus. That's like a relative E plus that you see here. So the difference, so Oscar pointed out, is non-canonical identification of this Z, but you see that the difference between two G2 structures is related to the positive Euler class of the co-bounding A-manifold. So now you can almost guess the definition of the new invariant. So that MS is the boundary of W T. So T and spin. Now this is going to definitely have zeros in general, and so this is what we define. But those, if you think about it, it's a relative Euler class. The number of zeros you get depends only on the topology of W. It's a bit of a mysterious number, but this is equal to the number of zeros. G.
Eta? Or what was it? Is it eta? N?
Oh, what am I doing? Sorry. Excuse me. So this is this is a number, positive number of zeros. The notation is a little bit tricky. It only depends on the spinor on the boundary. That's the point. It depends on the topology of W and the spinor on the boundary.
It's called N plus or what?
Yeah, N plus because to make sure by convention we associate it with this E plus over here. And now we can define U of one of these spinors, which is the same thing as the G2 structure. If I take such a co-boundary, which always exists, we take this number modulo 4k. Now, why is this a good thing to do? Well, suppose I had an M and a diffeomorphism between them, spin diffeomorphism. Well, this would bound to W, and this would bound to W. To get the orientation right, maybe let's make this negative. Okay. The Euler characteristic is going to add, because this is an odd dimensional manifold, its Euler characteristic is 0, the signature adds, that's another called additivity, and the zeros will add because I changed orientation here. So the spinor field here in the column neighborhood has no zeros, so these zeros out here. So what this thing is doing is it's trying to compute, if I'm not mistaken, minus 48 times the A root genus. And that's why this is well defined 1 to 48. Good.
Is the A roof genus of an...
So this is in quotes. I'm saying
Yes,
that
if it's closed, the roof genus has not the visibilities. I mean, can you get rid of this?
so if I take this expression and evaluated it for a closed W, I would get, by a map characteristic class formula over there, minus 48 times the A root genus.
Okay.
This thing here would be the E plus. Yeah. So that's what I mean by these square codes. So that means when I glue it up, that will mean that the answer I get, so there's choices of co-boundaries in this diffeomorphism might shift things, but the ambiguity, well, up to modulo 48, that's what we're on. So the theorem with Nordstrom, this is the properties of U. So yeah, let me now define E2 of M with a bar on it. E2 of M modulo the spin diffeomorphism, so we're just calling that E of M. We're in the spin category. So what we get is a well-defined invariant. U is a well-defined invariant from the honest topological moduli space, which is very modulo 48. It's very good at counting this difference invariant. So once you normalize things, this is twice the difference element. And that's coming in here because we had put a 2 here. And it's coming from this factor of 2 in this characteristic class formula here. I mean, if you just take one of your spinners and do something on the 7th sphere to add an extra rack around the 7th sphere, when you propagate that over the W, it's at exactly 1 point here, which then gets doubled in the formula. So that means, in fact, that if you look at the equation modulo 2, you just see here, if you look modulo 2, you just see the Euler characteristic of W and the signature to W, and that's a simple thing, that's just the rational semi-characteristic. So U of S is equivalent to the sum of the Betty knots. 0 to 3 IM. That's the statement modulo 2. But in particular, so Thomas has done a good job of emphasizing that it's good to verify that your invariants are non-zero. But in fact, we have that now, right? Because this difference jump, I can make a jump of 1 here, so it just jumps by 2. So that means that this topological moduli space has at least 24 components.
I mean, it's not expected that this number actually does not depend on n. Right? I mean, this is for any n.
It's for any n.
But you don't expect the actual number.
That's exactly what I'm going to talk about now. Yeah, so the actual number, it's once you have an invariant, you'd like to know under what circumstances it's a complete invariant. That's the subject of the next subsection, which is called counting D2 structures. So let's just count the left-hand side. And when I say a count, so I just introduced some terminology of my co-author. So definition a deformation of G2 structures is a homotopy. It's the equivalence relation generated by homotopy of G2 structures and diffeomorphism, spin diffeomorphism. So this thing here is the number of deformation equivalence classes. That's just language. Yeah, so now I want to take up this question and try and relate this to reactivity. So there's an action here, as I was, here's where it's good to have perhaps a different definition of this D2 structure. So remember that this is non-canonically equivalent to Z. And so I'll take now I want to think of a G2 structure as a lift in Oscar's sense. That would be the easiest way to do this, and just act. Okay, so here now I'm thinking of a G2 structure as a map from some universal G2 bubble.
Does the diffeomorphism group of M act on the spinor bundles?
Yeah, I was thinking about that. It's not completely clear.
No, it's not. I don't think it's true. You take a spin diffeomorphism group.
Yeah. So maybe you need to lift it up. Yeah.
And also there might be some bad component. I know it's simply connected, so.
In the next lecture, we'll define a G2 structure as a free form, and then this would be good. We just pull the free form back. So you do need to be flexible, but for this particular notion of a G2 structure, if I have my diffeomorphism, I can just do the obvious thing. Yeah. So we'd like to understand this action, because that's exactly, we know that this action, so this is a translation action, and somehow the theorem over there says, so that this has to happen by jumps of 24, right? So if I have G2 structure here, L, well, let's call it 5, then I know I have to jump at least by multiples of 24. But what property of M? It must be a property of M that controls this. The number of G2 structures on M is an invariant of the underlying spin manifold. So which invariant is it? Okay, well, it's time to bring in our friendly mapping torus. So here's a copy of M, and here's another copy of M. Here's one G2 structure. Now I want to think of it as a spinor. And by this translation, first translate it to a canonical G2 structure in this sense, do your diffeomorphism, then think of it as a spinor again. I've got these two guys here. Now I can close this up on the one side as the mapping torus. Okay? So here I'll glue by F. Okay? So this is compatible, right? Here there's a nice path, and in here I'll just do what I did before, right? Remember, so here's my G2 structure here, and here I'll just choose a path between them and it'll have some zeros. So I choose an interpolating spinor. Okay? So the number of zeros here, this interpolating spinor here, that is my difference element. But it's also the positive Euler characteristic of this mapping torus, which is a spin 7 manifold. Yeah? So if we thought about this, we can see that the difference of the spinor and S star S, this is exactly the positive Euler characteristic of the mapping torus. And if I'm lucky, I haven't erased the formula, which is right here. Good. You see that the Euler characteristic of a mapping torus and its signature vanish, so we can just forget about them. And that means we've now got, this is, and I think I have to, for some reason, I get confused about the signs, but I believe that in fact there's a minus sign. But now we're getting close to reactivity, because you remember for a mapping torus, the A-roof genus, well, that's a function of p squared, and the signature is 0. So this is proportional to p squared, right? And the reactivity exactly measured the possible values of p squared for a mapping torus. So whatever the possible values I can get for all mapping tori here is exactly controlled by the reactivity. Now it's more linear algebra. Okay. So this is minus 4. Yeah, well, I wrote that already. Plus some stuff at 0. And in fact, that is minus 24. I'll just, so remember, I want to abbreviate p squared at a mapping torus. Johannes asked me about this last lecture, and I wrote about last lecture. So remember, this is by definition p of the mapping torus squared. So it must be that when you do the algebra, the number of G2 structures is determined by the reactivity.
Where does the 224 come from?
Yeah, this is this A-roof genus factor.
Oh, I see.
So this is the expression for the A-roof genus. Yeah, this miracle characteristic class formula. So, right. So, let's look at the smooth reactivity. Remember, we defined reactivity for almost diffeomorphisms because we wanted to look at these homotopy spheres. But you can do the same thing. We can just define this to be p squared of diffeom. And if you think about the formulas, that's going to be, well, if I have an almost diffeomorphism, or if a diffeomorphism, that's in particular almost diffeomorphism, going in the other direction, the yoga gives you this miracle. So remember that this was in 8z, and that this number here is 8 times 28. So that's where this 28 homotopy spheres come from. So that gives you, and remember for a 2-connected 7-manifold, we computed the reactivity. So, so M2 connected. Then the topological moduli space has precisely the following number of components. Take the numerator of 2 to the r u0 of m divided by 224. And, okay, maybe the details, oh yeah, so you recall that R was something that depended only on the fourth cohomologies, the linking form in the Pontryagin class, and it lived in 0, 1, and 2. And D naught was this funny divisibility. In particular, if Pm is 0 rationally, then D naught is 0. So numerator is 0, okay, and you need to reinterpret the formula so it says Z. So, well, yeah, infinity times Z. Okay, so this is D naught, not 0. And the answer is you get Z if D naught is 0. Okay.
I think we should never think of D naught can't be 0, it's divisibility. Right?
Yeah, we said it to be
Always
0. We said it to be 0 if the Pontryagin class is rationally trivial.
You just said it to be infinity in that case, and then you don't have to keep making case distinctions.
Then yeah, maybe that's right. Maybe we should set it to be infinity. That's a good point. 0 is infinitely divisible. Huh. Yeah, that's a good point. We should renormalize.
D naught is an infinity in this numerator form.
What's the divisibility of 0? What 0 divisible by?
I'll just point out another corollary. So, so for M2 connected, and D, okay. Right. Let's say M2 connected, D divides 112 and R equals 1. So this is R equals 1 is basically what happens most of the time. So I'll just say that this is generic. For example, for these manifolds that we introduced previous lecture, these guys here. So this was a certain sphere bundle. Then in this case, D0 is just D and R equals 1. And in this case, then U is a complete invariant.
That's nothing but plugging in the numbers.
Yeah, it's nothing but plugging in the numbers. The sort of point is there's this translation that you can make. The more divisible your Pontryagin class is, the bigger the jumps are, but the smoothness tells you your Pontryagin class has to be at least this divisible. Sorry. Let's try that again. When you make these jumps, sometimes the jump you're doing is an almost diffeomorphism, it's not an honest diffeomorphism. So that gets ruled out. So that's the sort of why there's this funny sort of clear lows on. In fact, for almost all of the holonomy G2 manifolds constructed, D is a divisor of 24. So when we want to apply this sort of calculation again to an honest full holonomy G2 manifold which is 2 connected, then we're in good business. Okay. So that's pleasing. We've got this topological moduli space. We've got a very good handle on how many components it has, and in the 2 connected case, we know exactly how many components it has. And in the next lecture, I'm going to talk to you about what that led to in terms of G2 geometry. But in the remaining 5 minutes, let me say just a little bit about this psi invariant. So, and that's the point. So the remark is that mu and mu of n are both A-root. So they're both given by taking a co-boundary and trying to compute its A-root genus in a certain way, and exploiting the fact that the A-root genus takes surprisingly, large. Is expressed in this, as this large denominator in its expression, or rather is an interval for a closed spin A manifold. So, what I want to try and give you is the slogan. So mu attempts to compute minus 48 A-root, and mu of m attempts to compute 28 A-root, the way things are normalized. And if I didn't screw up, there should be a linear relation here, right? So I think this is 7 times 4. And this is 3 times 16, so I think the difference is 12. So in this sense, that means that you would like to define psi to be 7 lots of mu and 12 mu. And then this, in some sense, should be identical to 0. And this actually works. So recall that we for a W we had a Gauss refinement, what we were calling a Gauss refinement on this SD pi. So SD pi was a certain subset of the fourth cohomology of M, and of course, as always, M is the boundary of W. And this was a function that lived in an appropriately normalized Q mod Z. Okay, so I feel that incidence and molecules and maybe I won't write out the definition because I don't have so long. I just at this level is somehow heuristic. But now if you take psi by definition, so this is now an invariant. This was a function. This is an invariant of a smooth structure. And if you map this to 7 times the expression for the new invariant, plus 12 times the expression for discount refinement, we have to multiply by 12 and get something in Q of 3 e pi tilde z. Okay, and yeah.
Where is the 3 come from?
I multiplied by 12. So GW was here, and I multiplied GW by 12. Yeah.
So S is still the,
Spinner, which is the G2 structure. This is our current notation for the G2 structure.
and nu depends on S, of course, but the GW doesn't really.
Yeah. Yeah, so as I said, the point was to, this was actually I was talking with Johannes about the way we develop the algebra for these GWs, and the point was to be extremely careful about where this residue took values. This is just when we were working on the generalized Diels-Quaker invariant. And I said, okay, we're taking all the care of this, what's the relationship of this to nu? Okay, and that was a great moment. You emailed back the next day and you said, well, there's this other invariant, and it does the job. So this was not something we were really looking for, but once we'd taken so much pain to get the two connected story exactly right, somehow it just became obvious that this was also an invariant. So that's the theorem I can finish with. So again, M2 connected. So now I want to associate the following data to a G2 manifold. I associate its fourth cohomology, this linking family. I don't need the generalized P of M. I don't need the generalized Diels-Quaker invariant anymore because I associate to it psi, nu, and psi. So this quadruple is a complete invariant. It's a complete. So these invariants, this is now actually all completely algebraic. This is just a residue. This is a function. Okay, this is algebraic. This is an element in this group. This is another function defined on a subset. So all of this is totally algebraic, and the theorems is before. So all of these guys are realized. And if you have an algebraic isomorphism of the invariants that preserves the invariants, it gets realized by a diffeomorphism that takes the G2 structures to the G2 structures. So that's that's in some sense, if you want to, that's a detecting factor for the category of two connected 7 manifold G2 structure. Okay.
So are there questions?
So you really do want to have these 5 variants now. So I mean, you have more structure, you manifolds have more structure, so more manifolds or more invariants is appropriate.
Yeah, right. I mean, on the 7th sphere, for example, there's an integer's worth of G2 structures that aren't visible, and they get seen by this psi invariant. So this guy here, this can only count 24 things. Sometimes there's many more than 24 things. So and the point is that this is the most compact way we can write it, because we also need this generalized Diels-Quaker invariant, but we can express that in terms of these two.
So just wondering about the logic of this. I mean, with this classification result, you should be able to get back to, given this classification and the classification of spin manifolds from last lecture, you should be able to get back
Yeah, right.
that result. So how are they logically dependent? Does that go into the proof, or does...
No, we got this invariant, and then you can do the algebra and you can see how many extra new G2 structures can psi count. Okay, and you just do the algebra and you see how many it is, and then you actually look at the reactivity and it tells you exactly how many they are.
Yeah, so that is more corollary with this.
No, for us this was first. We computed the reactivity before we even knew psi existed.
But we can make it a corollary.
Yeah, we could make it a corollary now, once you have the definition, but I think this is primary because in somewhere in here there's actually topology, and it's in this afternoon's exercises. You have to build almost diffeomorphisms and diffeomorphisms of 7 manifolds to prove this. So that might actually be some sort of slogan about classical surgery theory, or even modified surgery theory, classify up to S-cobordisms. S-cobordisms are basically diffeomorphisms. Take two cylinders and glue them together. Those two theories will not build diffeomorphisms for you. So if you need to go the full 9 yards, then you need to actually build diffeomorphisms on your manifold. So I push surgery as hard as I can to see it, and so far as I can tell, it doesn't. So an important part of this whole project is the manifolds are simple enough, you just build the diffeomorphisms you need. But surgery theory doesn't tell you whether diffeomorphisms in that sense exist. Self-diffeomorphisms, that's something you have to do for yourself. Yeah.
If I start with a G2 structure as such a spinor field, you can take minus it.
Yeah.
Is it the same G2 structure or is it different?
Yeah, it's the same one, because this is a beautiful theorem. So the G2 structure, I should have said this, the G2 structure actually takes the spinor bundle and writes it as the trivial line bundle plus the tangent bundle. That's because if you look at G2 sitting inside of spin 7, then you actually get the standard, so you have this unit 1, and you get an induced representation of G2 on these imaginary nocturnals. So this is a beautiful fact. A G2 structure, this is one reason why you should like G2 structures, it identifies the tangent bundle of any spin 7 manifold with the Octonians. So I am going to answer your question here. So it's a theorem of Massey maybe that this tangent bundle of any oriented 7 manifold has 2 vector fields. So there's certainly enough room in here to rotate the plus spinor to the minus spinor around. But that's that's another feature of 7 manifolds. Yeah.
So what? Oh,
Go ahead.
what you said about these things occurring as a boundary of an 8 manifold.
Mm-hmm.
So basically, what you have there is a sort of curvy calculus description of these things in terms of 3 spheres and a 7 sphere.
Yep.
Right.
Right.
There should be a question.
Well, it's sort of a little bit, from the point of view of curvy calculus, I like it. A little bit disappointing because, okay, I mean, that's good. That's exactly right. We've got 3 spheres in S7, but we know we have so much room. So that in terms of a link, we now have a link, and the link has a lambda, a linking matrix associated to it. And there's also a framing, right? These are embedded, so for each component you get a framing. And that's basically what's behind Wall's classification. That's it. So this gives you the self-intersection, this gives you the link of the trace, and unfortunately there's nothing more. Now I hadn't thought about this in the G2 world. I don't know if there's, we never really thought about G2 surgery and whether there's a slightly richer category of G2 links.
Well, I guess the question would be, can you identify in terms of links when part of the link is inessential? In other words, you could improve the Buddhism, reduce the relative readiness of the Buddhism by throwing away part of the link. Could you see that in the link?
In the link picture, I think so, yeah. I mean, if you have a part of the link which the link is disjoint, doesn't link the rest. And it's like, in curvy patterns, you always throw that away, right? Because that's a CP2 off to the side.
Well, that's, maybe the question is, could you run this backwards to get a really detailed picture of more sophisticated ways that you might pull apart lengths or that they don't really interact or something like that.
Well, I don't know.
It's not really a question.
Just
You don't
a
have to
question.
really answer.
Yeah, all right. I will just say that, okay, one way to compute the 7-dimensional L group is to show that every quadratic refinement arises as the boundary of a form. So that computation of the L group would basically wall set all of the Q's I have and just wrote down the lambdas. So that's some sense a model set of links in a 3-sphere that give you every 7-manifold, if you want to say it that way. There's actually a consequence, all right, yeah, if you have a tree and label it with these bundles, you also get such a lambda. It's the theorem of David Race that if the link is presented by a tree, the boundary has positive Ricci curvature. So we just wrote a paper in which we showed that every one of these Q's gets presented by a lambda which has a tree, and that was a non-trivial amount of work. So that's something maybe in this direction of what sort of links you can show.
Okay, maybe we can ask more questions during the discussion.